Hello again, this is Structural Analysis and Design made fun and easy. This is Structural Steelwork Design, the BS5950 brace short column. No, this is a simple case, just very simple, concentric axial load, just to get started. This is now part 5 of 6. Please like the video and subscribe to the channel. Please donate if you can to let me make more videos like this. So in part, I've done factored loading, a bit about concentric load, load combinations, and then checking the local buckling of the section, working out the plastic, what section type the section is, like plastic, compact, semi-compact, ratios of the web and the flanges to the breadth and the depth. And then I've done, in the last video we looked at buckling about x-axis. So this is part, please watch the other videos and then you can see all the good work that I did. This is now buckling about y-axis. So to start off, it says about the y-axis, it says as per the x-axis, the restraints top and bottom held in position. So if you just watch the other videos when I go through the question, but that means top and bottom held in position. That means it can't move, so that means it pinned, and then it says but also partially restrained in direction. So okay, so let's look at buckling about the y-axis in this grid system first. So consider that this is not the answer to the question, because it says in the question this is also partially restrained in direction. I'll do that in a second, but let's just say for now that in y-axis, let's look at how it works in y-axis because of the column orientation and how it buckles. So look at the diagram here. This is the actual load on it's drawn a little bit wrong. I've drawn it as an I-beam, but it should be an H section. So what happens is it will buckle about y. So that basically means it's going to go this way. So it will go along, it will buckle, so the displacement will take place along the x-axis. That's at 90 degrees to the y-axis. Then the maximum displacement will take place again as it's buckling under h over 2. So there. So in this I'm just trying to explain a bit about the orientation and which axis is stronger. So basically, a beam is double symmetric, but it's not fully symmetric. So because in one orientation, in the x-axis, when it buckles about x-axis, you have the two flanges to make it the two flanges and very deep web, so it will be stiffer when it buckles about xx, because you got the web is parallel to the y-axis, but when it buckles about y-axis, you got the flanges which are parallel to the x-axis. So the web is in the same. The web of the beam is parallel to the y-axis. So that means it's going to be weaker because it's going to buckle like this. So the web in this time, the web's going to buckle like that again. The flanges will be stronger in the y-axis in 2, but so in the above isometric 3D left example, take one flange of usage to show the plane of the bending. Let's say, like for example, on this one, it's going to buckle about that axis. So this is generally called weaker axis, isn't it? To determine which part of the UC is strongest in this direction with these axis orientation, i.e. not the flanges, the web in the case. So oh yeah, to demonstrate which part of the UC is strongest. In this case, in this direction with these axes, it will be the flanges. Will be the flanges, and not the web. The web in this direction, and buckling about YY, because of the way the because the YY axis is parallel to the web and on the same line, that means the web's going to be very weak. So that's when we look at the column's capacity, we need to be aware that that it's going to be weaker about this axis. Although this question has a little twist because the restraint conditions are different. So this question is a little bit tricky because in the XX axis is pinned, so that's LE equals 1. But so now let's look at what the actual effective length is. So in this case, in the XX direction for buckling, sorry, this should be Y. In the Y, so in the YY direction, for buckling about the YY axis, in my opinion, that means effect, because it says held in, it says, what is it? Held in position, so that means it's pinned, but also partially restrained in direction. So that means it's partially fixed. So in this diagram, I tried to draw it. It's a bit hard to draw it in Word because Word isn't really a drawing program. So it wouldn't be, like fully, the ends won't be fully vertical, but they would only deflect a little bit, and then it'll buckle between those points which have deflected. So I've tried to draw it as best I can. Just say that it moves like the top of it moves. Say the top of the column, the top and the bottom of the column, they can move say 5 or 10 degrees, and then the rest of it's free to move. It's partially restrained in direction. So that means, to me, it's partially fixed. And that seems a bit weird because I don't know. I need to do a little bit more research, to be honest. I don't know how that's. I mean, it could be it's braced or not. In practice, it could be braced frame, partially braced frame. But in this case, so the the effective length is gonna buckle mainly between there and there, and the effective length factor is effective height 0.85h. So the effective height is 0.85 the total length. As I just tried to draw it, just do zoom. Yeah, you see it a bit better there. I just say a buckle between there and there. This little bit is partially held in direction at the top and the bottom. Mostly it buckles about here. So again, you have the maximum displacement about the DX axis in elastic, and then when it fails in plastic failure, the DZ you get, this is going to deflect. So you have deflection in DZ and DX. This is the X deflection this way, and then the Z deflection will be down. So that's basically we got LE equals 0.8 for the restraint position. So it's held in position, top and bottom, partially restrained in direction, top and bottom. So therefore LE equals 0.85 L. 0.85 times 6 is 5.1. So now we got the effective length factors. So, sorry, that should be LEY or LEYY. LEYY, and we already know from before that I worked out that LEX is 1 times L is 6 meters. So then we can move on to the next stage, which is designing. Now we're going to design the column. It doesn't actually ask for this in the question, but I just want, while I'm doing effective length, might as well explain that. Not in the question, but if it was fixed at both ends, LE, let's say X or Y, if it was fixed in direction, LE would be 0.7 L as a buckle like this. This would be the buckle pattern. So it'll be straight, and then it'll buckle between those positions, somewhere in the middle of somewhere symmetrically in the height, with the maximum dx or dy would be again maximum in the middle, and the effective height would then be 0.7 h. But if you go to BS5950, that you've got, it works out all the effective height factors. It's all in there. I might do a separate video just on effective heights, because there's quite a few combinations, and it can be quite confusing actually if you don't know, if you're just getting started up and you don't know. I didn't really understand it when I started, to be honest. So this is the end of part 5. So hopefully see you in part 6, where now I've finally designed the actual column for actual load. If you want to, I've covered in the other videos. Please watch part 1 to 4. Please like and subscribe. They are the ones where I did the loading, the ultimate loading, the load combinations, the buckling, local buckling of the section, and then these last 2 videos I've been on working out the effective height. Please donate if you can to allow me to do more videos. Thanks for watching.